Let's take a look at what that closure looks like. Well, if we take a look at G, we can see it has an underscore closure method. In fact, that was one of the arguments that we had to pass into types.function type to create a function, or we could optionally pass into types.function type to create a function. We can see that that closure is a tuple of cell objects. If we go into one of those cell objects, we can look at its contents, and in fact, its contents are the value of y that will be used when we evaluate G. It is important to note that when this function is created, when this G function is created, we're not capturing a reference to the closed over variable as it existed as of the creation of this function. Instead, there is a necessary indirection. This closure cell is an entity that we need to pay attention to, and it represents an indirection from the function to what was in that enclosing environment. Let me show you what I mean. Here we have G0 and G1, which are two functions that are created that close over X that's provided in their defining environment by F. If we take a look at their closures, we will see that they share this cell object. It's not that we created one cell object for G0. It's not that we captured a reference to X in G0 and captured a reference to X in G1. But we created a cell, which is an indirection to X. And in G0, we have that cell, and in G1, we have exactly the same cell. And they point to exactly the same integer, which means if we happen to have some mutable data that was shared between two things, it was closed over and shared between these two functions, well, it stands to reason that that will be visible from both functions. That is to say, G0 and G1 are going to be operating on the exact same mutable x's. So when I call G0 and it doesn't append, I'll see that append visible on G1. However, it may not be as readily clear to you that if this value is immutable, we'll see the same behavior. There's one small detail that's different here. Because this value is immutable and because the Python parser doesn't try that hard to do scope determination, therefore when it sees x equals x times 2, it says x equals must be a local variable, incorrectly guesses a local variable, and it then needs to be corrected with this non-local keyword. But beyond that, what I want to impress upon you is this x variable is not just some shared mutable reference. It's actually an indirect reference through that cell object. And so, in this particular case, when G0 performs some mutation on its closed over X, it's not performing a mutation on a copy that it was given. It's not performing a mutation on some reference that it was given where it's now going to change that reference because obviously this integer is immutable, so it can't change the integer in place. It's instead going to go back into that closure cell and update what's inside that closure cell. And so G0 and G1 will share the same closure. In fact, if we take a look at this, we'll see as we step through this, they have the same closure object, they have the same cell, and it's merely the case that that int object that cell indirects them to is being updated as we perform these manipulations. This is why sometimes you'll see some brain teasers where somebody will do something like define a bunch of functions in a loop that close over something, and they'll say, okay, depending on how I call these resulting things all at once or one at a time, I get some different results. It's not that much of a brain teaser if you think these functions are live referring to that closure cell, which means if you have a loop that defines a function, then calls it, defines a function, then calls it, defines a function, then calls it, and in between updates that closure variable, well, each function call will give you some different output. If you have a function that defines, put that into a list, and then calls all of them, and you only mutate the thing that they refer to as you go, well, you'll see that all of them refer to the resulting value because they're not referring to the thing as you step through. You're not capturing a snapshot as you step through. You're capturing a live reference to the original cell, which means you can get some very different outputs in those cases. And you have to be aware of what's the relationship between when things are called, when things are evaluated, and how that closure may be updated. Now, these are notes that will be important later. Let's take a step back and think a little bit about functions and when it is that we write functions. And so here we have a fairly simple data processing framework. And it's pretty much the case that in this data processing framework, I'm going to operate on, say, random data. I'm going to generate some data. I'm going to perform some normalization, like a z-scoring of this data. I'm going to process this data by identifying which elements of the data start with a certain letter. There's name-value pairs. So all the values that start with a certain letter. And then I'm going to do some reporting on that data. I'm going to tell you what the minimum value that I saw and the maximum value that I saw. Now, there are a couple of design flaws in this code, and I'm sure that you can spot them. For example, this code is fairly short, And as a consequence of being fairly short, there's a question for do we really want to generate data in this fashion? Because it stands to reason that details like the number of letters in the name or the range of these values or the total number of values are all really going to end up being modalities of generate data, and this could start getting quite complex. Whereas if I just left this inline, then I don't really need to worry too much, because if somebody needs to change one of these items, they don't have to change for these modalities. So it stands to reason that maybe generating the data might actually not be a good use of a function. For normalizing data, everything is fine. For processing the data, this is actually not that much code, but maybe there's an argument to be made why this looks the way it does. But for reporting this data, you can imagine, well, there's a lot of customization that somebody is going to want to do on this report. They're going to want to change the digits of precision. They're going to want to change what is reported. They're going to want to change the formatting. They're going to want to change where the report goes, to the console, maybe to an email, to a database. Here, it's just printing to the console. Maybe they don't want that. Well, setting aside all of those design flaws, we're going to imagine that this library is a popular library, and as a consequence, it's in use in two places in our code base other than in library.py. It's in script 0 and script 1, and we can see some repetition. Many of you have been told that the key principle for writing functions is DRY. Do not repeat yourself. That is wrong. If you eliminate all repetition in your code by writing functions, you're going to discover that you'll end up with code that is far, far more painful to manipulate, far more painful to extend. Instead, what we should look at is anytime there's repetition in our code, what is the nature of that repetition? Is it the case that this repetition is wholly coincidental? It just happens to be the case that these two blocks of code with generate the data, normalize the data, process the data, and report just happen to look the same? Or is it the case that they must always necessarily be the same? Is this coincidental or is this intentional? And then based off of that, we can determine whether or not we want to write a function. Because here you can see an example of somebody saying, well, it's repetitive, so what I'm going to do is I'm just going to write a function and I'm going to reduce the total number of lines of code that I have. And yet, if it happened to be the case that this was coincidental repetition, then it stands to reason, by virtue of me saying there's coincidental repetition, that these two scripts may diverge over time. Here's a way where they could diverge over time. Somebody could come to you and say, you know what? I don't want to normalize the data anymore. This user, the person who wrote this, doesn't want to normalize the data, but this user still does, which means we have to create a keyword argument here, and we have to pass that keyword argument here, and then determine whether or not we perform the normalization. Somebody else could say, you know what? I actually want to customize the printing a little bit. And in fact, if you think about it, anytime we interact with the outside world is going to be a hotspot where somebody's going to say, actually, I don't want to do what everybody else does. I don't want my data that is read in to be formatted as a CSV. I want it to be a JSON. I don't want it to be a JSON with these keys. I want to change the keys very slightly. I don't want it to be JSON. I want it to be JSON embedded in something else. You need to do some additional pre-processing. I don't want it to be printed out in this particular fashion. I want it to be emailed in some other fashion. Well, anytime we interact with the outside world, there's a risk that our stakeholder is going to want to have some ad hoc changes that only ever apply to them. And so here you can see another case of that, where somebody has said they want to customize the digits of precision for this report, which means we have to create a keyword argument here, and we have to pass in that keyword argument here, and then we have to update this report here to have that keyword argument. If we had left this code as it originally stood, if we had left it as just repetitive code, we would have found that all of these divergencies, all of these changes would have been very easy to address without us having to thread new arguments in and making all of these pieces more complicated. They would have reduced our additional retesting burden, because anytime we change existing code that is used by multiple users, we need to validate that that change didn't affect our other users, didn't cause any other unintended consequences. And in this particular case where the change was not at the surface level, was not one level deep, but was now 2 levels deep, well, the fan out of the things that we have to check now or verify or validate are still accurate, still correct, is going to be quite large. If we had left this code as in the repetitive form, we may have found that we can then superficialize these changes, where the changes need to be made are now very superficial, and we don't have to do that revalidation. And we can allow these code to diverge. Now, this is, in fact, what we might say is the characteristic of coincidental repetition that has then been unified into a function. If we think about a function as a single source of truth, then it stands to reason that anytime we see repetition in our code, we should ask ourselves, why is this repetitive? Because if it changes in one place, it must then consequently change everywhere else, or because it just happens to look this way right now. And if it must change in one place, or a change in one place must cascade to all places, that's a function. If they may diverge readily, that may not be a function, at least not yet, until we find the pattern by which a change in one place corresponds to a change everywhere else.
Thanks for watching. If you enjoyed this video, give it a like, hit subscribe, and check out the recommended video on the screen. See you in the next one.